Okay, let's see a couple of examples on components of we are discussing microwave components. So far we have discussed 3 basic components. We have discussed directional coupler, we have discussed power dividers and hybrid circuits, and last class we have discussed circulator. So to summarize what we have discussed, let's see a couple of examples. So the first example, circulator is given. This circulator, as you can see, it has 2 specifications. So the first, so this circulator has insertion loss, as you can see from the slide. It has insertion loss of 3 dB. And here you see this circulator has insertion loss of 3 dB. So that's given for this circulator. Insertion loss how much? 3 dB is given. Okay, and second specification you see is isolation. So isolation for this particular circulator is 60 dB. So when you have any circulator, first you have to check whether it is clockwise or anti-clockwise circulator. So as you can see here, the arrow indicates this is anti-clockwise circulator. We have discussed a circulator is used to guide a signal to the required port, right? So in this case, it is anti-clockwise. So when a signal comes at port number 1 as input here, where will be the required destination? Because this is anti-clockwise, it should go to port number 2 and must go the output here. So port number 1, the output will be port number 2 because this is anti-clockwise circulator. Now if a signal comes from port number 2 as input, where will be the output? Signal will be guided in the anti-clockwise direction, and here should be the output, port number 3. Now what will happen if signal comes from port number 3 as input? Where will be the output? The output, because signal will be guided in the anti-clockwise direction, and the next port is port number 1 will be the output. This is how a circulator works. So the first thing we have to know, is it clockwise or anti-clockwise? So we have to know which input port, which will be the output port. So we have discussed a circulator is 3-port device which is used to guide a signal in the required direction. So if this is anti-clockwise circulator like this, if you connect the signal from port number 2, it's guided, and here is the output. It will not go and it will not go to port number 3. If a signal comes from port number 3 as input, because this is anti-clockwise, it will be guided here and you will get it out. So it's anti-clockwise circulator. circulator 3-port device. Okay. So when a signal guided in the correct direction, this is port number 1, this is port number 2, as you can see here, 3 ports are here. So let's say this is anti-clockwise circulator. So this is the arrow. So if input comes at port number 2, inside this there is a magnetic material. So the magnetic field of the ferrite material inside the circulator guide this signal from port number 2 only to port number 1, right? So if signal goes from port number 2 to port number 1, it is the correct direction. In this case, only we have a loss, what we call it insertion loss. Insertion loss. What is insertion loss? As we have discussed, any device, any passive device has some, it absorbs the signal. So there is some attenuation when you transmit the signal to a component. Some part of power is lost, right? Due to the component itself, we lose some power. That we call it insertion loss. We have discussed so many times. So this is a circulator, also a device. So if you apply some amount of power here, input power, where will be the output? The output you will get it here, P out. So when you compare P input and P out, there is some loss here. That loss we call it insertion loss. Okay. Another thing here, this device is not perfect. There is a leakage. Signal will go in the wrong port. In this case, if a signal goes from port 2 to port 3 as output, is wrong, right? We need this circulator to guide all the signal from port 2 to port 1 only. But there is a leakage. Small amount of power go in the wrong direction to port number 3 as output. That's what we call it isolation. When you buy a circulator, you have to consider these two specifications. What is the first one? The first one is insertion loss. When a signal transmits in the correct direction, how much signal loss due to the components attenuation. How much good quality the circulator is. If it is good quality, the only very minute small amount of power go in the wrong direction. All the signal must be guided in the correct direction. That's what we need from a circulator. Okay, but as I said, there is always some design imperfection which cause some problem. So what does it mean, this leakage means? Now look here. Transmitter is connected to port number 1. Our antenna is connected at port number 2. Receiver is here, which is connected at port number 3. This is our circulator. What type of? It is clockwise now. So if signal comes from transmitter side, port 1, where do you get the outputs? The output must be guided. This transmitter signal must be guided in clockwise way. When you go clockwise, which port you get? 2. So this is the output, port number 2. So all the transmitter frequency will go to port 2. What's port 2? Our antenna. So it will be transmitted. If signal received by the antenna is connected at port 2, so it's circulator, clockwise circulator. So this go clockwise. Which port you get? 3. So all signal comes from the antenna, go to port number 3, our receiver. This is what we expect from the circulator. Okay. without interference of the transmitted receive frequency. Same antenna, as you can see here, shared by the transmitter and receiver. Transmitter signal transmitted, receive signal go to the receiver simultaneously. So this circulator here is used as a duplexer. Okay, but as I said, these circulators are not perfect. So if you transmit 10 gigahertz transmitter frequency, TX, if you receive 1 gigahertz, sorry, 12 gigahertz, just as an example, 12 gigahertz frequency, received frequency, this is TX, this is RX. So this 12 gigahertz transmitter signal must go only to the antenna and transmit it. But on the receiver side, you will find the 10 gigahertz also. Why this 10 gigahertz comes to the receiver? If this device circulator is not good quality, the 10 gigahertz, instead of going to port 2, small amount will come in the wrong direction to the receiver. How much frequency? 10 gigahertz. The receiver only needs the 12 gigahertz, which comes from the antenna side, right? But the 10 gigahertz transmitter also comes, which causes interference. Our own transmitter causes interference on the receiver. Because of what? Because of the leakage from the circulator. That's what we call it isolation. Okay? So the higher isolation the circulator has, it has better quality. The higher the isolation is better. So let's say example of this. So let's see here this example. So this circulator has insertion loss of 3 dB, as I said, insertion loss 3 dB. What is insertion loss means? Insertion loss means, as you can see here, loss through a device when you go from port 1 to port 2 of each device. Okay, so this is what anti-clockwise circulator. So if signal comes from port 1, if it goes to port 2, it's the direction we need. In that case, we call it what? Insertion loss. Okay, but there is also what we call it isolation. It's the reverse, unwanted transmission of our signal in the opposite direction. That's what we call it isolation. So this circulator has isolation 60. Okay, so when you buy a circulator, we need minimum insertion loss. The minimum the insertion loss is better. The higher isolation is better. So if you compare two circulators with isolation 40 dB and another circulator with isolation 60 dB, which isolation is better, the 40 dB or the 60 dB? The 60 dB isolation is better, which means very small leakage. When I say leakage, a signal will go in the wrong port. It will be very small when isolation is high. So the higher the isolation, it's good quality of the circulator. But insertion loss, again, is attenuation by the component. So we need it to minimize as much as possible. Okay, so these are given. What were asked? If 30 dBm signal is put to port 1, now P1 is how much? 30 dBm signal. You know, dBm is a unit of power. So 30 dBm applied here at port 1. 30 dBm. Okay. Now the question is, what power at port 2 and port 3? How much power you get here, how much power you get here as output. So P2 solution, P2 is a required port or not? Because this is anti-clockwise circulator. If signal comes at port 1, it must guide it to port 2. So it's the required direction. We need all the 30 dBm here. But there is what? There is insertion loss of how much? 3 dB. So input 30 dBm at port 1, 30 dBm, minus how much power we lose? Insertion loss 3 dB. You see, if you are using dBm term, the analysis, as I said in chapter 1, is very simple. So if P1 is 30 dBm input, how much power we get at port number 2? 27 dBm. So why we subtract only 3? Because signal go in the correct direction. Now how much power we get at port P3? If the circulator is a perfect device, isolation will be infinity. The higher isolation, as I said, is very good, which means isolation is infinity. No power will be here. P3 should be 0. All the power must go to port number 2. But as I said, due to design or manufacturing imperfection, there is always signal goes in the unwanted direction. In that case, the input is 30 dBm. How much power we subtract? How much? The isolation. How much is isolation for this circulator? It is 60 dB. Okay. So how much it is? Minus 30 dBm. It's very small power. If you convert it into milliwatt, you can see this is 0.00 something because it is negative. Negative dBm is less than 1 milliwatt. Okay, so to calculate P2, we subtract insertion loss. To calculate P3, we subtract isolation. Because P3 is unwanted direction, you have to subtract the isolation. If signal goes in the correct direction, we'll subtract the insertion loss. Okay, let's see another example. Example 2. This circuit, this figure, as you can see, it's a transceiver, which means this system transmit and receive simultaneously using circulator here as a duplexer. So this is our circulator here. Let's analyze this circuit. So let's start from the transmitter part. We'll see, let's see individually this component. Okay, this transceiver. So in the transmitter section, here you see this, we start from it's an oscillator, microwave oscillator. We'll discuss this oscillator later. So that is the oscillator. This oscillator generates our signal 10 gigahertz frequency and 100 milliwatt power. Okay, so this oscillator generates our signal power 100 milliwatt. Okay, 100 milliwatt power and a frequency of 10 gigahertz. That's the our microwave oscillator. Microwave oscillators we discuss next time. So this is the symbol for oscillator. Okay. Now this signal go to next device. Our next device is what is the symbol of this? We have discussed this device. It's called directional coupler. Okay, this is our coupler. So the first device, the oscillator, microwave oscillator, it generates signal with power 100 milliwatt and a frequency of how much? 10 gigahertz. Okay, that's our oscillator. First device. Our first device is the oscillator. Okay, next device is directional coupler. Okay, our next device is directional coupler. So this device, directional coupler, as shown in the diagram, is coupler. This is electrical symbol for a coupler. How many ports it has? 4 ports. Input port P1, direct port P2. What's P3? We call it coupled port, and isolated port P4. Right? It's 4-port device, directional coupler. So as given on the specification here, this coupler has coupling, which is C. How much? 10 dB. This coupler is 10 dB coupler. The specification is given. Another given directivity is infinity. So directivity is infinity. And insertion loss for this coupler is 0. No loss due to the coupler. Okay, these are given for the directional coupler. Okay, what's the next device in our transmitter? This parametric amplifier. The output of the directional coupler go to the this parametric amplifier. The next device is the parametric amplifier. This parametric amplifier has a gain of 8 dB. How much? 8 dB. Okay. This is third device we have here, a parametric amplifier. This is what? Directional coupler. This is oscillator. Then we have here the filter. After amplification, the signal goes to a filter. We'll discuss microwave filters next time. So in this case, this filter, another device, we call it a filter, has how much loss? Loss of 1 dB given. So it has loss of 1 dB. Okay. Then the filter output goes to what? Goes to our circulator. As you can see here, this is the clockwise circulator. It is clockwise circulator. Port 1, port 2 connected to the antenna. Okay, this is transmitter section of the system. This is a transceiver. So it has transmitter section. As you can see here, start from the oscillator. Our signal go to coupler, go to amplifier, go to filter, circulator, guide the signal to the antenna, and it transmitted. Okay, it transmitted. Now, this is our filter. So how many components? One remains, the circulator. In the transmitter side of our system, we have all these devices. Start from oscillator, directional coupler, second device, amplifier, third device, filter, fourth device, circulator, the fifth device. Start from one oscillator. So 5 components connected in series until it reaches the antenna. So the circulator, this circulator has given here. The circulator has insertion loss of how much? 1 dB. Okay, insertion loss. You know what's insertion loss of a circulator? 1 dB. Okay, isolation. Isolation is given for this circulator 50 dB. Okay, isolation I. When signal go in the wrong direction, we subtract 50 dB. When the signal goes in the correct direction, only we lose 1 dB. That is our circulator. How many devices? 1, 2, 3, 4, 5. Okay. Now the question is, here we are asked 2 questions. Signal generates, the oscillator generates 50 milliwatt, 10 gigahertz. Now it passes through coupler, it goes through amplifier, goes through filter, goes to circulator, and transmitted. So the question, first question is, how much power is transmitted by the antenna? How much power is transmitted by the antenna? PT. That's the question. Okay, so to get that, here 100 milliwatt power comes. Well, what's the next device? It is a coupler. This is P1. P2 goes here, right? P3 is here. Coupler divide the signal into 2 parts. The signal P1, which comes from the oscillator, as you can see in this diagram, signal which comes from the oscillator comes to the coupler. So the coupler divides the signal into 2. Right, as we have discussed before, coupler takes small amount of power to port number 3. The remaining transmitted directly. So in this case, let's see how much power is diverted. So from our coupler, how much is C? C is 10 dB. 10 dB coupler, as we have discussed, coupling means what? 10 log of P3, sorry, P1 divided by P3. Okay, so we have discussed this formula. Coupling indicates for directional coupler how much power is transferred to port number 3, P3. P1 is given now. How much is P1? Signal comes from the oscillator side. 100 milliwatt power is come from the oscillator side connected to port number 1, P1 input power. This P1 divided into 2, P2 and P3. So let's calculate P3. How to calculate P3? We get it from what? From coupling C. Directional coupler C indicates how much power is coupled. So how much C is here? For our coupler, C is 10 dB. C is given. So you can calculate 10 log of, you can calculate what? P1 is given 100 milliwatt, right? 100 milliwatt. So you can calculate P3, how much power coupled and go to port number 3. So you can divide by both sides by 10, both sides by 10. So this 10 gets cancelled, this 10 becomes 1. So to remove the logarithm, this is the base 10. So we make 10 the power of 1 will be 100 milliwatt divided by P3. Right? So from here you can calculate how much power go to port number P3, which is how much? 100 divided by 10, 10 milliwatt. Okay. So from our coupler, from C, now we have 10 milliwatt go to port number 3. How much input? 100 milliwatt. How much go to port 3? 10 milliwatt is sampled 10 milliwatt. Another specification, look here. Directivity is infinity. So when signal coupled through a directional coupler, some part will go in the wrong direction, which is called isolation port, right? But in this case, because directivity is infinity, there is no coupling in the wrong direction. All the coupled signal go to port number P3. And this coupler has no insertion loss. Insertion loss is also 0. Directivity is infinity. So how much will be P2? P2 will be P1 input power minus P3 coupled power in the correct direction minus P4 coupled power in the wrong direction minus insertion loss. This is our formula, right? Insertion loss. So look, if you apply 100 milliwatt as input, some power go to port 3, some power go to P4, some power is lost. Now, no loss, no coupling in the wrong direction. These are 0. So what remains? P1 minus P3. P1 is how much? 100 milliwatt input power from our oscillator minus 10 milliwatt, sorry, which goes to port number 3. You can see here this coupler input power divided into 2. So P2 transmitted in our transmitter circuit. This coupler takes small power P3, 10 milliwatt, go to the receiver side for our mixer. It divides the signal into 2. Okay, so how much? 100 minus 10 will be 90 milliwatt. Okay. This is the power at here. Look here. So this 100 milliwatt power, 90 milliwatt comes here. How about the 10 milliwatt? 10 milliwatt coupled, sampled in the port number P3 by what? By our coupler. 90 plus 10, 100. The 100 watt divided into 2. Now this 90 milliwatt goes through amplifier, go to the filter, go to the circulator, and it's transmitted by the antenna. Okay, so to do this analysis, it's better to convert this milliwatt into dBm. So as we have discussed in chapter 1, dBm is equal to what? 10 log of the given power 90 milliwatt. Okay, 90 milliwatts divided by 1 milliwatt. Do you remember the dBm formula? Okay, so 1 milliwatt get cancelled, so it will be 10 log of 90. How much in dBm? Let's use our calculator. So it is 19.5. So this will be 19.5 dBm. Okay, so here P2 is how much? 19.5 dBm. So in this case, at this point, we have 19.5 dBm. Okay. This 100 watt divided into 2, 90 will go transmitted directly, 10 coupled in the. How do you get this? From the coupling C. So convert this 90 milliwatt into dBm. Why we convert milliwatt? Because dBm is very much simple. Then what's the next device? The amplifier. So this 19.5 dBm power, which comes from the coupler, what's the next device? Amplifier. So it will be a gain of how much? 8. So the amplifier, our amplifier here has gain of 8. So we have 19.5 dBm minus or plus? Plus 8. Why we plus? Because it is gain. Amplifiers has gain 8 dB. What's the next device? A filter. So what is the power here? Filter has not gain but a loss of 1 dB. So loss means you have to subtract. So minus 1 dB because of the filter. Here you see our filter here. What's the next device? Next device, circulator. Okay. Now in this circulator, signal comes from this side, port 1, go to port 2. Is this the correct direction or wrong direction? Here, if signal comes from the filter side, port 1, go to port number 2, it is clockwise circulator, so it follows the correct direction to the antenna. So in this case, which one we subtract? Insertion loss or isolation? We subtract insertion loss. This circulator has insertion loss of 1 dB. It is given insertion loss 1 dB. So minus 1 dB from the circulator. What is insertion loss? When signal guided in the correct direction, some amount of power we lose. So this will give us, what? PT. The power, look here, we start from the oscillator, 100 milliwatt, divided into 2, 90 milliwatt from the coupler. 90 we convert into dBm, 19.5. This one amplified by amplifier. When it goes through the filter, we lose. When it goes through the circulator, we lose. So we get how much power transmitted. How much? This power, 19.5 minus 6, so PT will be 13.5 dBm hour. You can convert this into milliwatt. This much power go reach what? Reach the antenna, PT. Reach the antenna. How much frequency? This 10 gigahertz frequency from the oscillator transmitted all through these circuits and radiated by the antenna into space. How much power reached the antenna? 13.5 dBm. You see, it's very simple. If it is gain, you have to add. If it is loss, you have to subtract. In this particular system, we have oscillator, which generates 100 milliwatt. The coupler divides the signal into two. Amplifier amplified the signal P2. Then the filter, there is a loss, 1 dB. Then circulator guide this signal to the antenna. Now, part B. This 10 gigahertz signal, is it going to the receiver side? Look here. Now we are transmitting a signal from oscillator, so it goes through amplifier, filter. It must go to the antenna side and transmit it. But this circulator, as I said, is not perfect. This 10 gigahertz signal from our transmitter side go to the receiver in the wrong direction. It causes a problem. In case of a radar, because of high power, this leakage will damage the receiver. If in high frequency, in high power telecom applications, we have to take care. This leakage must be very minimum of 0. Otherwise, this high transmitted power from our own transmitter signal, instead of going to the antenna, the antenna will transmit, but there is also this signal comes, our own transmitter signal comes to the receiver. We don't need this 10 gigahertz. This receiver is designed to receive what? The incoming signal, 10.1 gigahertz from the antenna side to come to the receiver. Because it is a transceiver, we need to transmit and receive simultaneously. So what we need, all the transmitter signal will go to the antenna only. All received signal go to the receiver only. This is what we need, but it's not always true. For in practical cases, there is a leakage. So how much power leakage from transmitter to the receiver? That's the next question. Leakage, power leakage. How much power from transmitter side? So we have to know how much power at port P1. How much? So here is 19.5, right? 19, sorry, from coupler we have 19.5 dBm. How much power here? We add 8. I think I made a mistake here. So here, plus 6, sorry, plus 6. 8 plus 6 will be 20, 25.5, not 13. 25, sorry, 25.5, because 19.5 from the coupler plus 8, it will be 27 minus 1, 26 minus 1, 26.5, 25.5 dBm transmitted power. Okay. So if you add 8, because this is gain, 19.5 dBm plus 8 will be 27.5 here. because of the amplifier. Then how much power here? We lose 1 dB, so 27 minus 5, we lose 1. It will be 26.5 dB. Now this input power is port P1. So how much power go to port 3? Leakage, unwanted power. That is what we call it isolation from the circulator, 50 dB. So 26.5, that's input at port 1, 26.5 minus what? Minus 50 dB. Isolation. Because the signal goes in the wrong direction, the circulator, we have to subtract isolation. Higher the isolation, it's very good. Small leakage. So how much it is? 23.5 negative. Sorry. Minus 23.5 dBm. The signal goes in the receiver. This much power go from the transmitter to the receiver. We call it a leakage power. It's called a leakage power.